Thank you very much for inviting me to give this keynote talk. This is a topic that I enjoy talking about a lot. And we're going to cover Rowhammer. I call it the story of Rowhammer because I think it's been an interesting story since we started working on it as early as 2012. So when I talk about Rowhammer to freshmen in my class, I actually show this picture of this bridge, and many people may know which bridge it is. This is the Tacoma Narrows Bridge that used to go over the Hood Canal. It was built in 1940, and it collapsed 6 months later, like this. And I think this is a really great example of a bit flip in critical infrastructure. And there are reasons, of course, why this bridge collapsed at that time. It's aerostatic flutter, and there's a lot of civil engineering classes that are taught upon that bridge. But I see this as an example reliability problem affecting safety, security, availability, and many things we hold potentially dear to our safety overall. And I think what I'm going to talk about is no different. And in fact, worse perhaps, because if you think about bridges are only a small fraction of what we rely on in the world, whereas computing is much bigger. We're going to rely much, much more on computing going into the future for making decisions for us, for driving for us, for who knows what else for us, for making health decisions for us. And if we keep having bit flips and reliability problems that affect our safety, security, availability, then we're going to have a lot of trouble. I also talk about this example of workers who are building New York City after the war, and they're clearly happy on this rod over here. But if a bit flip happens on this rod, they will not be very happy very quickly, right? So I think of security as preventing unforeseen consequences. And as you build critical infrastructure that relies on the security of your devices, I think this is a really good way of thinking about security going forward. So Rowhammer is one example of this bit flip that may be affecting critical infrastructure. So what is Rowhammer? It's essentially the fact that you can predictably induce bit flips in commodity DRAM main memory chips today. And more than 80% of the chips that are out in the field is vulnerable. This is, in my opinion, as far as I could find, this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I'd be happy to see other examples of this if you have something in mind. And it's interesting because a lot of folks who think about software are now saying, forget software. Now hackers are exploiting physics. And I think at a high level, this is a nice characterization of what Rowhammer is about. So I'm going to tell you a story. I'm not going to directly jump into the Rowhammer, but I'm going to describe how it happened and where it's going into the future. So when we first started looking into reliability issues in main memory, I was asked to deliver this invited talk at the International Memory Workshop, which is a heavily industry-dominated workshop. And I talked about essentially memory scaling. And I said that memory technology scaling is getting much worse, and we're going to have a lot of problems. At that time, we didn't have a lot of evidence, hard evidence from the field. And then we were collecting evidence, and unfortunately, it didn't go into this paper because it was not ready. But what we were looking at was the DRAM scaling problem. And it was clear to us that we will have a lot of problems. So why? If you look at DRAM, it's basically the main memory technology that we use to build essentially all of our main memories with today. And it consists of two components, the storage unit, which is the capacitor in DRAM because it's charge-based memory, and then access unit, which consists of this access transistor, bit line, and the sense amplifier. And for any memory to work, sorry about this, for any memory to work, both the storage unit must work and the access unit must work. And unfortunately, as you reduce the size of the memory, both the storage and access unit becomes less reliable. In DRAM, the capacitor must be large enough for reliable sensing. The access transistor must be large enough for low leakage and high retention time. And as you reduce the size of both, you run into noise issues and reliability issues that may cause a lot of difficult problems, as I will describe. And in 2009, when International Technology Roadmap of Semiconductors wrote their report, they said that scaling this technology below 35 nanometers is challenging. And they were actually essentially right on this one because Rowhammer happened, and there are a lot of other things happened, as we will see. So we did some experiments in the field together with Facebook. This is one example experiment that we have done. Well, it's more like a correlational study. We studied all of the memory errors that happened in Facebook's data centers for more than 1.5 years. which is reported in this paper in DSN in 2015. And what we found out was that the chip density that's employed in a server highly correlates with the server failure rate that you observe on that server. This is the chip density in terms of DRAM chip density, essentially how dense your memory is. So this is a correlational study. This is based on production data center servers. We couldn't modify what was going on. You can read the paper for more detail. But the intuition is that as your chips get denser, they become more vulnerable to noise, and you get more errors, bit errors essentially, because cells are closer to each other and they're more vulnerable to noise. Okay, there's more to talk about here, which is exciting, I think, but I don't have time to discuss that. So we also wanted to understand these scaling effects at the lower level. So we built FPGA-based testing infrastructures that look like this to understand the problems that we have in terms of the scaling of the memory technology. So we looked at retention errors, for example. We looked at read disturb errors, which I'm going to talk about. We looked at latency issues. What happens when you actually change the latencies? And that was enabled by this FPGA-based infrastructure that allowed us to test the memories. And you can see some pictures of what we have created. And we released this infrastructure to the community with this HPCA paper. And it's actually C++ programmable. As long as you have an FPGA that is compatible, you can use our software to test memories, and you can find different sources of errors potentially. Sorry about this, but somehow my computer is moving by itself, and it's not because of the settings in PowerPoint. There's some sensitivity in my mouse, I think. It's a new computer. Okay, so if you're interested, we actually open source it, and we provide a lot of support for it. A lot of people in the world are using it for various reasons and publishing papers with it. So the main reason why we built this infrastructure was to really understand the data retention effects. And data retention is how long can data be retained in a DRAM cell. And I believe this is a critical scaling problem of DRAM. And we wanted to understand how can we make data be retained longer in DRAM, or how do we get away without refreshing DRAM much? Because it's actually a big performance and energy problem that affects the scalability of the memory capacity significantly. So that's the reason why we built this infrastructure, and we wanted to understand the retention time profile of DRAM. And it turns out it looks like this. We're refreshing everything about every 64 milliseconds today. But most DRAM cells actually don't require refresh for much longer than that. But the difficulty is this is location dependent, stored value dependent, time dependent. So a lot of our research was focused on understanding how we can get rid of refresh in DRAM as much as possible without causing reliability issues. And I'm not going to talk about that. This is a fascinating direction. And you can read some papers that we've written on this topic. And there are more papers that are coming up. It's actually a very, very interesting problem, in my opinion. But that was essentially the reason why we built this infrastructure. But while we were doing all of those studies, we were actually very, very interested in other error types that occur in DRAM, especially the read disturb errors, because we also had a similar infrastructure with flash memory. And in flash memory, we saw a lot of read disturb errors. I'm going to show you the picture of that infrastructure later on during this talk. We saw that you get a lot of read disturb errors in flash memory. We asked the question, why don't you get a lot of read disturb errors in DRAM as well? And that's essentially what we did together with Intel. We investigated the possibility of read disturb errors in DRAM, and we found out that you can predictably induce errors in most DRAM memory chips by inducing this read disturb phenomenon that I'm going to talk about. So this is called DRAM Rowhammer. As I said earlier, it's a simple hardware failure mechanism that can create a widespread system security vulnerability. We're going to talk about the system security vulnerability soon, and you can see what I showed you earlier. So what is the problem? The problem essentially is very fundamental. As long as you have a scaled memory technology, in my opinion, you're not going to be immune to read disturb. And DRAM is nothing special. As it scales to smaller technology nodes, it's going to be vulnerable to read disturb. And what is read disturb in DRAM? Essentially, if you want to access a cell in a row in DRAM, you apply high voltage to that row, which is activating that row. You activate that row. And then you need to close that row to access some other row. Basically, you apply low voltage after that. This is called a pre-charge on DRAM. So if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times before the cells get refreshed in modern DRAM, it turns out you get bit flips in physically adjacent rows in bits that are vulnerable to this Rowhammer or read disturb effect. Clearly, this should not happen because you're not writing to DRAM, and you're clearly not writing to the adjacent rows. You're not writing to the row that you're hammering, But you're also not writing to the rows that are victims. So this should not be happening, clearly. So you're violating physical isolation and also virtual isolation as well. And we showed that more than 80% of the chips that we tested from 3 major DRAM manufacturers exhibited this vulnerability. And you can guess who these A, B, C are. There are only 3 major DRAM manufacturers in the world today, which may be an unfortunate phenomenon, but that's how it is. So this is a scaling problem because the chips that we tested that were manufactured before 2010 were not vulnerable to this effect. But all of the chips that we tested that were manufactured between 2012 and 2013, as you can see, were vulnerable. So you could see varying Rowhammer error rates, and it's really manufacturer independent. So why were the older chips not vulnerable? Because you couldn't do enough activates to induce these bit flips. The cells were not close to each other. At some point, the cells got too close to each other that by doing activates in one row, you could induce noise, enough noise in adjacent rows, and you could fit in enough activates to cause these Rowhammer bit flips within a refresh interval before the cells get refreshed. Okay, so I think I gave you the idea of why it's really happening. It's sorry, is there a question? I hear some noise in the background. Okay.
No, I don't think so.
Okay, thanks. So the DRAM cells are essentially too close to each other. Access to one cell affects the value in nearby cells due to electrical interference between the cells and the wires used for accessing the cells. And that's essentially the read disturbance that I talked about. This is also called cell-to-cell coupling or interference. So there are multiple reasons for it. I'm going to briefly flash a slide that talks about the reasons. I'm not going to go talk about the details, but essentially an intuitive reason at a high level is when we apply high voltage to a row, an adjacent row gets slightly activated as well. And vulnerable cells in that slightly activated row lose a little bit of charge. And if you do this activation enough times or hammering enough times, charge in such cells get drained before the cells get refreshed. And higher level implications are a bit scary. Essentially, DRAM, as I said, is not special because it's not immune to read disturb, but it is very special actually because whatever bit flip you get in DRAM directly gets exposed to your programs. It directly gets exposed to your data structures, operating system, applications. As a result, you have essentially no protection against these bit flips. So certainly you can get data corruption. Your system can halt for some reason because you get a bit flip on a critical data structure. And worse yet, somebody can actually take advantage of these bit flips to take over your system, as we will talk about. And this all happens because you can induce these bit flips predictably in software with user-level programs. So this is the user-level program that we released when we actually published the paper. It's a very simple program. You can see x86 program. You could actually optimize it by getting rid of this mfence down there. It's really not necessary. But basically what this program does is it selects addresses X and Y that map to the same bank in DRAM. And it avoids cache hits. It avoids row hits so that it could basically ping pong or interleave activates to rows X and Y like this. And it basically keeps activating rows X and Y. And if the chip is vulnerable, you'll get bit flips in the banks. And based on this program, clearly you can cause a lot of issues. And at the time we tested, we used Intel and AMD systems, but there's nothing special about Intel and AMD. This happens in any system that has a good enough memory controller and vulnerable memory. And essentially all systems have good enough memory controllers. Vulnerable memory we will discuss. And you can see that you can induce enough errors, and errors are correlated with the access rate that you're getting. And there are interesting questions we can have on why you're getting higher access rates on some systems and not higher access rate on some other systems. But basically, this is a real reliability and security issue. It's essentially a reliability issue that leads to a security problem. So I'm going to talk about the security implications next. When we wrote the paper in 2014, well, we wrote it in 2012, actually. It got published in 2014. But basically, the first sentence we used was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I still strongly believe this. And we said that by taking advantage of the bit flips, the predictable bit flips that we have shown in this work, somebody can actually hijack your system. And while we were actually working on this, the good folks at Google Project Zero, Mike Seaborn and Thomas Dullian, they basically published this beautiful blog post that essentially did that. They basically exploited the DRAM Rowhammer mechanism to gain kernel privileges. And I'd encourage you to read their blog post as well as watch their Black Hat presentation. It's a beautiful one. This slide essentially is copy pasted from their blog post. But basically, they learned about the problem from our work, and they tested a selection of laptops and replicated the problem. And they basically built two working privilege escalation exploits. One is taking over the Google native client. The other is more interesting, in my opinion. Essentially, it uses these Rowhammer-induced bit flips to gain kernel privileges on an x86-64 Linux, a vanilla x86-64 Linux, when it's run as an unprivileged user-level process. And I'm not going to go into the details of exactly how they did it. It's beautiful security engineering. But basically, they were able to induce bit flips in this process's page table entries. And they were able to change the page table entries such that they could gain write access to the process's own page table. Now, if you have a user-level process and if it gains write access to its own page table, then all bets are off, because now this process can be completely malicious and it can actually take over the entire system. Essentially, your system is completely compromised. And again, I point you to the Black Hat presentation by these folks. It's beautiful security engineering. It's a probabilistic attack. It's not completely deterministic, because you cannot always get the bit flips clearly. But we will talk about that a little bit later as well. So this is known as Rowhammer vulnerability, and people are drawing nice pictures like this, as you can see. And they're interesting comments from hackers. This is a comment on Twitter from a famous hacker. It basically says that it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. It's actually interesting. I like this analogy quite a bit. And interesting, just a side story. Initially, DRAM manufacturers were really not interested in talking about this problem, even after we published it and showed it many, many times. Later, they started calling this problem noisy neighbor problem, which also is interesting, I think. Now, I'm not really married to Rowhammer, but I think noisy neighbor is quite interesting as well. Okay, so I will very quickly go over some interesting security-related works that happened on Rowhammer, and then focus on some work that has happened later on. But basically, there's a lot of work. I'm not going to talk about these in detail. There's work that looked at cache line flush-free Rowhammer, because cache line flush instructions could be privileged in some architectures. And clearly, these works show that you can induce cache line. You can get rid of cache hits for these vulnerable, for these aggressor rows by actually causing conflicts in the cache clearly. There are also other works that showed essentially the same thing concurrently. And there are some example exploits that look at owning a system with all defenses up, even if the software is free, as you can see over here on Microsoft Edge systems. There are actually really interesting ideas here that combine memory deduplication and Rowhammer together. I don't have time to talk about all of these works, but I'm just going to show you some. If these slides will be available, so you can actually look at these works. I'm going to point to some of them later on. Actually, let me skip this. Let me go to one thing that I will talk about in a little bit more detail. So when we first actually released our work, the first people who were really interested in this was the testing, memory testing folks. And memtest86 is a program that is used by many, many systems to test main memory periodically, or when you boot up the system, or when you put up memory in the system. And they essentially designed a hammer test, which I think is not complete, frankly, due to the reasons that I'm going to talk about in a little bit also. But even without that complete test, they got a lot of errors. They basically got a lot of reports from folks in the field. And they had to write this in their online documentation. They had to say basically the errors detected during test 13, albeit exposed only in extreme memory access cases, are most certainly real errors. So they had to reassure people that what they're getting is real. It's not something that's made up. It's not a bug in their software, essentially. And they talk about some solutions, which we will also talk about. So our ISCA 2014 paper talked about some security implications that I already talked about, actually. We built a proof of concept, and later work actually showed that you could actually do this security attack. And I'm going to highlight several of these over here. These folks from TU Graz, for example, showed that you could do these attacks in JavaScript, and you could gain unrestricted access to systems of website visitors. These folks from Vrije University of Amsterdam, this is actually really interesting work. They basically showed that you could do these bit flips in ARM-based Android systems. And they actually released a tool that you can download, I believe. And what they did was they were able to gain control of an Android phone deterministically. They were able to fool the operating system to essentially allocate a page table entry for a malicious process in the location that the malicious process profiled to be Rowhammer vulnerable. And then the malicious process actually hammered that location to gain control of the smartphone by gaining write access to its page tables. So it's beautiful security engineering, as you can see. And this also showed that ARM-based systems are also vulnerable. They're not immune. Later work showed that you could actually do this attack much more heavily, intensively on GPUs, because GPUs have much faster access to memory, clearly, and higher bandwidth access. And some other work showed that you could actually induce these bit flips on a remote machine through the remote direct memory access interface and take over that remote machine through this RDMA interface. And this is concurrent work with that one. And more recent work showed that even if you may not be able to gain access, you can leak confidential information from adjacent rows or rows that you're actually targeting. And some other recent work showed that actually, if you carefully induce these bit flips in machine learning applications and neural network accelerators, your accuracy can tank to very low levels. So this work is more recent in Unix security, as you can see. They basically show that by carefully doing Rowhammer attacks on neural network accelerators, you can reduce your accuracy from 90% to 10% in an otherwise good neural network. And there are other works that I'm not going to talk about. And this may be another attack that may come up if you're actually too much constrained by these bit flips. Of course, that's a joke, clearly. This could be a solution also, getting rid of your vulnerable computer, right? So let's go into a little bit more detail in terms of understanding Rowhammer, and then I'm going to talk about solutions. So very quickly, this happens due to a multitude of reasons. I'm not going to talk about these in detail, but electromagnetic coupling, as I mentioned earlier, is one reason. Conductor bridges that get formed is another reason, and even hot carrier injections actually happen due to Rowhammer in some cases. But it's usually a complex combination of these effects, and we have actually confirmed this with two major manufacturers. This was an old slide, as you can see. So we used our testing infrastructure for many studies in Rowhammer, and we initially in 2012 to 2014 timeframe, we tested more than 120 modules that are listed over here, as you can see. I'm going to give you some insights from our characterization very quickly. The first insight is that the aggressor row and the victim rows are most of the time adjacent to each other. So this is the row address difference from the perspective of the memory controller. So memory controller looks at hammers row address X, and it gets bit flips in row addresses X plus 1 and X minus 1. But sometimes it also gets bit flips in non-adjacent rows. So there are multiple reasons over here. The main reason is that memory controller does not know the address mapping scheme that's used internally in DRAM. Not in all cases, address X and address X minus 1 and X plus 1 are adjacent to each other, physically adjacent to each other in DRAM, because DRAM manufacturers employ many internal swizzling mechanisms to actually change the accesses, remapping mechanisms to remap the addresses that is visible to the memory controller for fault tolerance reasons. For example, if a row doesn't work, they actually remap that row to some other physical row. So this actually complicates the solutions and sometimes the attacks. I'm not going to go into this detail, but I think this is actually a really interesting phenomenon. The second phenomenon is if you actually, the access interval to the aggressor, how fast are you accessing the aggressor, activating? So DRAM standards don't allow it below some nanoseconds, as you can see over here. If you're accessing at the highest possible activation rates, you get the highest number of errors, as you can see from the chips that are the worst chips that we tested from 3 major manufacturers. Clearly, by reducing the access interval, you can get rid of the errors. But this is not a good mechanism, at least if done naively, because if you do it naively and if you bake it to the standard, you actually need to get rid of, if you want to get rid of all of the bit flips, you want to reduce your access rate significantly and separate your accesses to a row by 500 nanoseconds, which is really not acceptable if you want to have high performance. But this is potentially one way of reducing the problem, as you can see. But if you do it naively, you won't get a good result because it will come at high performance loss. Okay, the third observation is refresh interval. Essentially, today, everything is refreshed every 64 milliseconds. And we get bit flips, you can see, if you're refreshing every 64 milliseconds. If you reduce your refresh rate, meaning make refreshes less frequent, you get more errors. If you increase your refresh rate, you get fewer errors. Clearly, because now you can fit fewer activates within a refresh interval. And if you fit fewer activates, then you reduce the probability of these bit flips. But our paper shows, as you can see, if you want to get rid of every single bit flip, you need to increase your refresh rate by 7x, which is not good for performance or energy, because we actually wanted to get rid of refreshes. Remember, that's the reason why we actually started this research, and that's a key DRAM scaling problem. We don't want to solve one DRAM scaling problem, which is Rowhammer, by exacerbating the other DRAM scaling problem, which I believe is more fundamental actually in the end. So this is not a good solution, but we will talk about this in a little bit. Okay, the data pattern is also important. So if you look at this left-hand side over here, if you have solid data patterns, if the adjacent rows and rows have the same data pattern, you get fewer errors. Whereas if they have different data patterns that increases the charge coupling between the rows, you get an order of magnitude more errors. So data pattern is a critical importance to the attacks as well. Okay, there are other results in the paper which I will quickly go over. Essentially, victim cells, Rowhammer vulnerable cells, are not the same as refresh or leaky cells, retention vulnerable cells. This is very interesting. These are different failure mechanisms. Even though one would intuitively think that a leaky cell is going to be more vulnerable to Rowhammer, that's not true, because Rowhammer phenomenon mechanism is very different. Even if a cell may not be leaky, it may not be vulnerable to Rowhammer, so it may not get a bit flip, even though it leaks a lot, right? Okay, so errors are not strongly affected by temperature, and we also found out that errors are repeatable, which is really what makes this a security problem, because if you induce a bit flip in a cell, you're going to induce that bit flip again and again and again and again. That's why this becomes a security problem. That way you can profile the memory and figure out which bits are vulnerable to these bit flips, and then you can try to induce those bit flips in the right time, in the right applications. Okay, we also showed that you can get as many as 4 errors per cache line. Essentially, simple ECC that may be employed in systems cannot prevent all errors, and you have to increase ECC strength, which is not a good idea, again, in my opinion, because ECC strength is ECC is a very heavy-handed solution to errors. In this case, in Rowhammer, we know why the error is happening, and we can design more specialized mechanisms to fix the errors. And we also showed that you can have many number of cells and rows affected by Aggressor. It's not just the physically adjacent rows, but as you go a little bit farther in terms of physical adjacency, you still get effects in terms of Rowhammer. The effect is not as bad as it would be for the immediately physically adjacent rows. It actually reduces exponentially, but still you can hammer non-physically adjacent rows also. We also showed that cells are affected by 2 aggressors on either side. So you can actually sandwich a row between 2 aggressors and hammer both of those aggressors, and the victim will have a lot more bit flips. And actually, this is used later by Google to develop the double-sided Rowhammer attack, which we did not introduce. So that's a good idea, I think, the double-sided Rowhammer attack. Okay, so first Rowhammer analysis in this paper. Let me talk about the Rowhammer solutions a little bit before I talk about the more recent work. So there are 2 types of solutions needed in Rowhammer, because clearly the chips that are out in the field are vulnerable. What do you do about them? These are immediate solutions. We need to protect the vulnerable chips, and there are limited possibilities. Longer-term solutions can be more aggressive and may have more options, and this is to protect the future DRAM chips. And in our paper, we introduced both types of solutions, 7 solutions in total. I'm going to talk about Para, which is already employed in the field, or it used to be employed until DRAM manufacturers claimed that they solved the problem, which we will talk about. So let's talk about some overall potential solutions. And these are solutions that I do not believe work, at least for the long run. Making better DRAM chips, that's not easy. Clearly, providing isolation between different rows is very costly. That would go against the capacity that we want in these chips. Refreshing frequently is one solution, and we'll talk about this as the immediate solution, but it's not a good solution in the long run because it will lead to power and performance implications. Sophisticated error correcting code is definitely a solution. You want to increase your error correction capabilities to 4 bits per cache line, which is very heavy, actually, costly and power inefficient. And as I said, this is not a good solution because error correction codes are great solutions if you do not know why the errors are happening, meaning errors are random bit flips. For example, soft errors. But Rowhammer is far from random. You know exactly why the errors are happening because you're hammering a row. So if you spend your error correction capability to these errors that are easy to detect and correct otherwise, then you will actually need to add a lot of ECC in your system, making your system much more costly and complicated and power inefficient. So access counters are also very interesting. Basically, can we somehow count the number of accesses that are seen by rows and basically throttle the accesses to those rows? If you do it naively, this could lead to significant cost, power, and complexity, but there could be potentially not so naive or more sophisticated mechanisms that could lead to good solutions here. And actually, research is being done in this direction that I will briefly mention later on, that tries to make these access counters less costly and the mechanism less costly. But I think this is not as easy to do, as we will see very briefly. So what is the solution that's employed in the field? Essentially, it's refreshing more frequently. You can see this is Apple's security release in 2015, I believe. They basically said that they mitigated the Rowhammer issue by increasing the memory refresh rates. They didn't say exactly how much. I believe it's 2x, which means that Rowhammer vulnerability still exists, because we showed that you need to increase the refresh rate by 7x. But clearly, I don't think they were willing to go to 7x, because that would have a huge impact on system performance and efficiency. And I like Apple here because they actually credit the academic work that led to their decision, as you can see over here. But many, many vendors actually release similar patches, because that's what you can do in the field today, refreshing more frequently. Any other solution is not easy to employ or impossible to employ, because you have to change the memory controllers or the chips. So let me talk about our best solution, at least at that time, to Rowhammer. And we call this probabilistic adjacent row activation. The idea is very, very simple. After closing a row, the memory controller activates one of its neighbors or both of its neighbors with very, very low probability, small probability like this. And you can change the probability based on your paranoia or based on what you know about the vulnerability of your DRAM chips. And we show that you get a great reliability guarantee that's much better than any other component in the system if you fix this probability to a reasonable level, as you can see. And as I said, you can change the reliability and security guarantee that you get by changing the value of P. So the advantage of Para is this is low power and low performance overhead, because you don't need to keep track of any rows over here. It's essentially stateless, low cost and low complexity. And we said that this is an effective and low overhead solution to prevent these disturbance errors. And I still believe that, actually, but I will show you some results from recent chips that show that the overheads of Para increases as the vulnerability of the chip increases. So this cannot be employed right away, because you need to either change the DRAM chip or the memory controller. So you could change the DRAM chip by doing these adjacent row refreshes by exploiting the timing and refresh parameter slack. And there's plenty of slack today. And actually, DRAM manufacturers do something similar in some of their DRAM chips today, but they cannot do it really well because there's not enough timing slack and there's not enough maneuver that they can have inside the DRAM chip. So I don't believe this is a good solution going into the future inside the DRAM chip, yes, at least by exploiting the DRAM timing parameters slack today. If you change the interface to the DRAM chip, it could potentially be a good solution, but that requires a JEDEC change in terms of interface. I believe a better solution is implementing in the memory controller. This requires better coordination between the memory controller and DRAM, and the memory controller needs to know which rows are physically adjacent. As I said earlier, memory controller doesn't necessarily have this information. Even though the rows are physically adjacent, memory controller may think that they're not physically adjacent because of the remapping that happens internally in the DRAM chips. That said, this solution was already employed by Intel in their memory controllers, as you can see over here. You can it's not exactly the solution that we envisioned, but it's very similar. You could actually adjust in the BIOS. Sorry about this. Pick your Rowhammer solution in your BIOS. You could either choose 2x refresh, as you can see over here, or hardware Rowhammer protection. If you go into the hardware Rowhammer protection, it's a mechanism called probabilistic refresh, adjacent row activation, essentially. And you can choose your probability, as you can see over here. And if you choose your probability wisely, then you can actually get rid of your vulnerability, in my opinion, but at the expense of performance overhead, of course. Okay, so I'm not going to talk about the old work anymore, but hopefully this sets the stage nicely so that we can talk about some of the work that happens in 2020. So my main takeaway is main memory needs intelligent controllers for security, and we will see that later on as well. And a very quick aside, I said that we do a lot of work on flash memory controllers, but if you look at flash memory controllers, there's a lot of intelligence to fix such reliability issues. So read disturb is clearly a problem in flash, but the memory controller in flash memory actually does a lot to avoid those read disturb issues because it has time. And if you're interested, I'm happy to talk about this further also. So I'm going to finish this part of the keynote by giving you some pointers. There's detailed lectures on Low-Hammer, and we've written some retrospective papers. This is the latest retrospective that we were invited to write on this special issue in top picks in hardware and embedded security for TCAD. But unfortunately, this paper doesn't contain what was done in 2020, which I'm going to talk about next, because I think what has happened in 2020 is quite exciting in terms of Rowhammer. It has shown that Rowhammer is becoming a much bigger problem and the solutions don't work. At least existing solutions don't work, which means that we need to take a more serious look at the problem again. Okay, I'm going to talk about two papers mainly, this one and this one. I'm going to start with TRRespass first, but we also wrote another paper that is very interesting in my opinion, that talks about can you somehow determine whether or qualify whether your DRAM module is or is not vulnerable to Rowhammer. And we tried very hard in this work to do this together with Microsoft Research. And the answer in the end is no, basically. At least with the testing mechanisms we know of today, it's very hard to do this. So there's room for qualification of DRAM modules also going into the future. Okay, let me talk about TRRespass quickly to show you that, to show you multiple things actually. So this is a work that was published in IEEE Security and Privacy, and we did this together with folks who have worked on Rowhammer from a security perspective a lot, from Vrije University in Amsterdam, and also Kaveh Razavi, who's at ETH right now. So what is the idea over here? This is the first work to show that target row refresh protected DRAM chips are vulnerable to Rowhammer in the field. So what is target row refresh? This is actually incorporated into the DRAM standard to solve Rowhammer. It basically says memory controller or the DRAM chip does something, and it's not clear exactly what that is, does something to mitigate Rowhammer. And these mitigations were advertised by DRAM manufacturers heavily as Rowhammer safe, saying that they fixed the Rowhammer problem. But this work showed that these mitigations that are advertised as secure are actually not secure. And the way it does is it introduces the many-sided Rowhammer attack, meaning that you can hammer many, many rows, not just 2 rows or 1 row. If you hammer many, many rows, you can bypass these mitigations that are put into place by the manufacturers. For example, by overflowing proprietary tables that detect these aggressor rows internally in the DRAM chip. And to be able to do that, we partially reverse engineered the existing TRR mechanisms implemented by the DRAM chips and memory controllers. And we do this by providing an automatic tool that can effectively create many-sided Rowhammer access patterns in DDR4 and LPDDR4 chips. So let me quickly go over what these access patterns look like. So this is one access pattern, for example. The red rows are the aggressor rows that you hammer. So in this case, it's a 3-sided Rowhammer. We call it assisted double-sided. And it turns out by doing this, you can bypass the mitigation mechanisms internally in some DRAM chips. This is a 4-sided Rowhammer. As you can see, you're hammering 4 rows. We will go up to as many as 19-sided and 20-sided. I'm not going to show the pictures of that, but you will see that later on. But these are some results from the field in real chips. You can see that for this chip from manufacturer C, you need to do at least 5-sided Rowhammer to get to bit flips. And later, you can also get to bit flips, as you can see. For this manufacturer, you need to do at least 7-sided. You need to do 9-sided for this manufacturer, as you can see, for this module. And you can see more detail in our paper. You can see 19-sided Rowhammer attacks, 9-sided Rowhammer attacks, and they vary in terms of their effectiveness, in terms of corruptions. And the paper has a lot more detail. And I believe the ones where we were not able to induce attacks are also vulnerable, in my opinion. We just weren't able to find the good attacks to be able to induce these bit flips. So we actually did this study on mobile phones also, and we found out that at least even with the limited capability of our tools at the time, we were able to induce these bit flips in real mobile phones that use LPDDR4 chips. So many folks thought that LPDDR4 and DDR4 chips are not vulnerable to Rowhammer because manufacturers fixed the problem, but clearly that is not correct. And we actually showed that you could get to the first bit flip very quickly, first exploitable bit flip very quickly. And you could actually, these are various types of attacks, page table entry attack that I mentioned earlier, RSA attack and pseudo attack. These are different attacks that are published in literature in terms of Rowhammer. And we see that you can get to the first bit flips in as low as 2.3 seconds, in some cases 3 hours. And you can essentially take over the system with these bit flips. So let me conclude with the key results. Essentially, we found out that more than about 13 of the 42 tested DDR4 DRAM modules are vulnerable. And you can see we did many different types of Rowhammer attacks. And 5 out of 13 mobile phones are vulnerable. And I believe these results are scratching the surface. Our tool is not exhaustive, and the paper also mentions that. And there are multiple reasons why it's not exhaustive. It's not easy to get to the best possible hammering patterns. And there's a lot of room for uncovering more vulnerable chips and phones, in my opinion. I believe actually all of the chips that we tested are somehow vulnerable because the mechanisms that are employed internally in the DRAM chips are actually not completely security proof because they're not proven to be secure. So basically, the key takeaway is Rowhammer is still an open problem. And the way manufacturers approach the problem to solve the security issue, which is security by obscurity, is likely not a good solution because someone will figure out how to unobscure the obscurity solution that you put into the security problem. Okay, there's a detailed lecture that talks more about the trespass that I'm not going to talk about right now. We don't have time, and you can certainly read the paper, or even better, perhaps download the source code and read the paper and improve the tool to show that you can do better. So let me talk about the other work, which is a completely different direction, but essentially leads to a similar conclusion. But the direction is, the study is done in a completely different way. So we call this revisiting Rowhammer. And this is a similar study to what we have done in 2012 to 2014, except we've done it with many, many more chips and many, many different types of chips. And we show that chips are still vulnerable. So basically, we characterize more than 1,500 DRAM chips of different types, technology nodes, and manufacturers using FPGA-based and SoC-based infrastructures. And we also studied 5 state-of-the-art Rowhammer mitigation mechanisms and an ideal refresh-based mechanism. Ideal refresh-based mechanism means that you minimize the refreshes. You do refreshes only when really absolutely necessary, additional refreshes. And there are 2 key observations in this work. First of all, Rowhammer is getting much worse, evidenced by data from the real chips in the field. It takes much fewer hammers, activates, to induce Rowhammer bit flips in newer chips, as low as 4.8K double-sided hammers. It used to be 139K in 2012, 2014. So we're about 2 orders of magnitude lower today. So vulnerability is increasing. And existing mitigation mechanisms do not scale to DRAM chips that are more vulnerable to Rowhammer, as we will see in a little bit. Basically, you get significant performance loss with Para. Para is actually a very nice mechanism that scales very nicely. But if you reduce the number of activates to induce bit flips to as low as 128, it leads to a very high performance loss. And we're getting there. We're slowly, well, maybe slowly or fastly, depending on your perspective, reference frame. We're getting closer to hundreds of bit flips, hundreds of activates causing bit flips. So basically, the conclusion is very similar to trespass. It's critical to do more research on Rowhammer and develop scalable mitigation mechanisms and secure mitigation mechanisms to prevent Rowhammer in future systems. Let me give you a little bit more insight into these results. Basically, we built 2 other infrastructures in addition to our DDR3-based infrastructure. We built a DDR4-based infrastructure that looks like this over here, and an LPDDR4 infrastructure for LPDDR4 chips so that we can do these studies. And we tested, as I said, more than 1,500 DRAM chips, as you can see, from 3 different DRAM types and 3 different manufacturers, as you can see. And some of the chips actually implement on-die ECC, error-correcting codes. We still see Rowhammer bit flips, even though the chips implement on-die error-correcting codes. That's not surprising, of course, because we know that some of the Rowhammer bit flips happen in as many as 4 bits, right? And there are 2 technology nodes per DRAM type, as you can see, old, new, 1X, 1Y. And we basically categorize DRAM chips in terms of DRAM type node configuration. It's a configuration describing the DRAM chips type and technology node generation, as you can see. So I'm going to cover some results relatively quickly. This is perhaps one of the most important results. This examines the hammer count effects. This basically looks at what happens as you increase the hammer count or reduce the hammer count, depending on where you go in the x-axis, to the bit flip rate that you get in different chip generations, DRAM type and node generations. And basically, Rowhammer bit flips increase when you go from old to new DDR4 technology node generations. The most clear example of this is the blue curve over here, which is the DDR4 old generation, and the yellow curve, DDR4 new generation. And the bit flip rate goes to the left and up with the new generation, as you can see, which means that Rowhammer bit flip rate increases at a given hammer count, right? Which means that the chip becomes more vulnerable. Okay, so, and that's true for different generations as well, which I'm not going to talk about over here. The other study that we did was the first Rowhammer bit flips per chip. What is the minimum hammer count required to cause the first bit flip in a chip? And you can see that we look at these results like this. There are 4 DDR3, DDR4, and LPDDR4 over here. And y-axis shows the hammer count, HC first, the hammer count needed for the first bit flip. So let's take a look at this example. For example, DDR4 chips over here, the hammer count you need in the old chips is relatively high. Let's say more than 80K, somewhere close to 100K. It goes down to 50K, 60K over here, as you can see. And that's true for DDR3 old. There are no bit flips in some DDR3 old chips, but some of the DDR3 new chips are more vulnerable, as you can see. And you can see that's true for many, many manufacturers and many, many DRAM type node configurations. Essentially, newer chips from a given DRAM manufacturer are more vulnerable to Rowhammer. And as I said, HC first reduces to some very, very small values. In LPDDR4, which is the most scaled chips that we've tested, it goes down to 4.8K double-sided Rowhammer. And essentially, there are chips whose weakest cells fail after only 4,800 hammers. Okay, so I've already said this. Basically, chips are more vulnerable, and you can get bit flips in more rows and farther away from the mid-term row as well. Now, let's take a look at how the mitigation mechanisms scale. So as I said, we studied 6 different mitigation mechanisms. Increased refresh rate is what's employed in the field today. Para, and I'm not going to talk about these different scaling mechanisms, but x-axis here shows HC first, number of hammers required to induce the first Rowhammer bit flip. It's high on the left side. It becomes lower on the right side. So right side is the future of the DRAM technology. We're going to scale to the right, basically. And y-axis is the system performance overhead of the mechanism that we're testing. As you can see, DDR3 old chips, HC first is somewhere here. LPDDR4, most scaled chips, HC first is here, and we're marching toward the right as we scale the technology. So basically, in today's systems, LPDDR4, existing mechanisms are not terrible. Basically, the overhead is about 8% with para, for example. But as you go into the future, only para's design scales to low values, but it comes with low system performance, very high overheads, basically. But ideal mechanism actually has a very good headroom. It's significantly better than any existing mechanism for a good number of HC first, which means that there's a significant opportunity for developing Rowhammer solution with low performance overhead. So basically, the future looks bleak, but we have a lot of hope because ideal mechanism is actually quite good. So we just need to approximate the ideal in the mechanisms that we develop. Okay, so basically, I've already said all of this. We need a low overhead and scalable mechanism. In my opinion, there are 2 promising directions for such mechanisms. One is DRAM system cooperation. I don't think we can afford DRAM manufacturers to basically take the problem and not treat it as a security problem and basically say we solved the problem. I think that's very dangerous because we are relying on this infrastructure for everything critical. We really need to cooperate between the DRAM and the system so that we can have a holistic solution that can prevent Rowhammer at a lower cost. And I think there's another direction which is really interesting, figuring out profiling mechanisms to detect Rowhammer bit flips. And we are very much in need for this fast and accurate profiling mechanism to figure out low Rowhammer bit flip detection. And I'm happy to talk about this more, but we don't have time clearly for that particular direction. And if you're interested, there's a detailed lecture on revisiting Rowhammer as well, and you can read the paper. So there's a lot more to talk about. I don't have time to talk about, but Rowhammer is getting even more interesting, especially with these works going forward. But Micro had multiple Rowhammer papers in 2020. There was a session in IEEE Security and Privacy dedicated to Rowhammer, as you can see over here. And as I mentioned, this paper, the neural networks are vulnerable to Rowhammer also. And I think this is going to be an interesting direction going forward. And we have a paper here coming up very soon that talks about another possible solution to Rowhammer that I don't have time to talk about. But I believe there's more to come in this, both in terms of the studies, vulnerabilities, and solutions. Now, let me quickly talk about future memory reliability and security challenges building on this. Essentially, what we have shown is that DRAM is becoming less reliable and more vulnerable. Due to difficulties in DRAM scaling and their detections, other problems may also appear, or they may be going unnoticed. Some errors may already be slipping into the field. Clearly, Rowhammer is one, and clearly we know that it's slipping into the field. But I believe retention errors are also similarly slipping into the field, except it's very hard to gather evidence to actually show that directly. Read errors and write errors may be slipping into the field, and who knows what else. And even if some of them may not be slipping into the field at this point, as scaling gets worse, they may be slipping into the field. Essentially, all of these errors that slip into the fields, they're reliability problems, but they can also pose security vulnerabilities because someone intelligent can take advantage of them. I'm not going to talk about those in detail, but I believe the solution is really building much more intelligence into the memory system, especially the controllers, so that we can handle these security problems. So let me talk about the solution direction at a high level quickly. How do we keep memory secure? It's DRAM clearly, but it's also flash memory and emerging memory technologies that are going to partially replace DRAM or flash memory have actually a lot of different error mechanisms that are somewhat scary. For example, phase change memory has write disturb mechanisms. STT-MRAM has other similar write disturb, read disturb mechanisms. But basically, I believe to solve these problems, we need to design fundamentally secure computing architectures. And
we somehow need to predict and prevent such safety, reliability, and security issues. And I have a 3-step methodology for this. I'm not going to go into the detail, and clearly I don't have answers in all of these over here. Sorry about this again. But basically, we first need to understand, then architect and design and test. I believe all parts need to do their job. Understanding is extremely important. We need to have methods for vulnerability modeling and discovery. We need to somehow model and predict based on real device data and analysis. And we need to understand the vulnerabilities and model them. We need to also develop reliable metrics. Architecting, once we understand things, once we model, once we predict things. For example, if we could have predicted Rowhammer if we could have modeled it right in the past, and we could have perhaps architected so that it doesn't slip into the field. But it did. But going to the future, maybe we can have principled architecture with security as key concern. We can partition the duties across the stack. DRAM, what does the DRAM chip provide? What does the memory controller provide? Clearly, we cannot give up performance and efficiency. And I believe patchability in the field, programmability and patchability of the memory controllers is going to be very, very important so that we can actually prevent some unforeseen consequences going forward. So design and test is also clearly important. We need to have principled design, automation, and online testing methods to discover these errors. That requires a design for security at the very low levels of the hardware. But this, of course, needs to interact nicely with the it needs to have high coverage and needs to have good interaction with system reliability methods. So what I believe we have shown is the understanding using experiments, and hopefully that understanding is very useful going into the future. And we have a lot of understanding built in flash memory also. And clearly the architecture mechanisms that I described are examples of principled architectures that distribute the work between the memory controller and memory in a good manner, so that memory doesn't need to have to do everything securely, such that the memory controller, which is much easier to control and verify, can be built more securely. Okay, let me go back to this picture that I showed you earlier. These are the bit flips in real infrastructure, bridges, right, that lead to hardware safety, security vulnerabilities, and potential attacks. Unfortunately, bridges are critical infrastructure, but they're very hard to patch. So this sort of bit flip happened in Seoul, in Minneapolis, in Genoa more recently, and there may be other examples as well. In that kind of infrastructure, we don't have the luxury of patchability easily, at least. Whereas in computing, we have a lot more flexibility in terms of finding out and fixing these problems if we're careful about how we design them into the future. And I believe in memory controllers, for example, we can have patchability. We can have online testing methods to detect some anomalous behavior and also issues that may come up, so that you can actually hot patch the memory controller in the field. Okay, let me give you some final thoughts on Rowhammer very quickly. I believe we have a few more minutes, right? Okay.
Yes, sure.
Yeah.
Okay, great. So let me give you some historical perspective and some conclusions and retrospective as well. So bit flips are actually very interesting. I really like this paper. I had read this paper much earlier. In fact, while I was a graduate student, I read this paper. This was written by folks at Princeton, and it was published in IEEE Security and Privacy. What these folks did was they were able to induce bit flips in physical memory by actually having physical access to the machine by heating up the memory. I will show you over here. They basically put a lamp into the memory and they heated up the memory and they induced bit flips. And they basically show that by doing so, you can take over the Java virtual machine. So this paper is very, very interesting. It's a bit ahead of its time, meaning that not many people are going to have this sort of access to a machine and heat up memory. And if you have physical access to a machine, and then maybe you can do much more interesting things to the machine potentially, right, to gain access. But this paper is really foreshadowing the importance of bit flips in security. What Rowhammer provided was a software controllable way of predictably inducing the bit flips. If you have a that it got rid of the physical access, it got rid of the difficulty of inducing bit flips at the right places, basically. And as a result, Rowhammer had a lot of impact into the thinking of the security community. And Rowhammer is an example of Byzantine failures. Very quickly, I will also I covered this in my class also. I borrowed this slide from Satya, who has done a lot of research on distributed systems at CMU. But basically, it's undetected erroneous computation. It's opposite of fail fast, clearly. And erroneous can be malicious as well. So whenever you have a bit flip, never think that it's just a bit flip, a reliability problem. It's really a security problem. And you may not know how to exploit it, but somebody else may. As a result, you really want to do all you can to avoid this sort of bit flips, because this is really a fundamental problem. It's a Byzantine failure. And it's very difficult to detect and confine these Byzantine failures. And if people are interested, I would definitely recommend Lamport's seminal paper on the Byzantine generals problem that was published in 1982, as you can see. So let me quickly revisit Rowhammer as a retrospective. I believe, as I showed you earlier, Rowhammer enables a new mindset that has created a renewed interest in hardware security attack research. Essentially, real memory chips are vulnerable to a great extent, and this causes real security problems. And hardware reliability and security connection is now mainstream discourse because you can induce these bit flips in software. Clearly, there are many new Rowhammer attacks that are being developed. I believe there's more to come, and I think they're also all very exciting. Clearly, we need many new Rowhammer solutions because there's more need for it, as I motivated in this work. I believe you need principled system DRAM co-design, for example, and I think there's more to come in this direction also. Perhaps most importantly, I think this shift of mindset, thinking that general purpose hardware is completely fallible in a widespread manner, enables a lot of interesting research, because now people think that the problems of hardware are actually exploitable. And I believe this mindset has enabled many system security researchers to examine hardware in more depth. Clearly, there were people examining hardware before, but now we have a lot more people examining hardware vulnerabilities. And they started understanding hardware's inner workings and vulnerabilities. And I believe it's no coincidence that two of the groups that discovered Meltdown and Spectre heavily worked on Rowhammer attacks before. And I know, and I worked with some of these folks also. And I believe there's more to come in that domain as well, not just Rowhammer, but vulnerability of hardware going into the future. So let me conclude. Clearly, memory reliability is reducing. Reliability issues open up security vulnerabilities, and these are very hard to defend against because this happens in the field. Rowhammer is a prime example, and it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. I think its implications on system security research are tremendous and exciting, along with computer architecture research. The bad news is Rowhammer is getting worse. There's no reason to believe that it's going to become better. Clearly, I present a lot of evidence to you. The good news is we have a lot more to do, and we know, I believe, what to do and how to do it, and in a better way, except we don't know exactly how to do it. We're now fully aware hardware is easily fallible. We're developing both attacks and solutions, both bit flips and otherwise. And hopefully, we're developing more principled models, methodologies, and solutions to fix the problem. This is where I'll conclude. You can read papers that we've written on the topic, and this is one slide that summarizes the detailed lectures. And I will finish with acknowledging people who funded this work. Please keep funding us, and acknowledging my students, many of whom have contributed to this work. And if you're interested, we released a recent newsletter that covers these Rowhammer papers in 2020, along with some other papers that we have worked on in 2020. With this, I will conclude, and I'm happy to take questions.
Thank you, Professor Mutlu, for the very interesting presentation. So we have some questions in the Q&A section. So I would maybe first address those, and then if there are any questions from the panelists, we can continue with that live. So the first question that came in is from Thomas Hoberg from Worldline, a financial service provider. His question is, would randomly swapping rows during refresh help, building on the defects handling logic already present in DRAM chips?
Yeah, so that's a great question, I think. I think there's a potential for this. You need to have enough rows, to spare rows, to actually do the copying of the hammered rows. But you also need to, I don't think random would work, frankly. Random is a bit difficult. And random can actually lead to a lot of overhead. If you do it in a targeted manner, meaning if you actually somehow detect a Rowhammer attack, when you're suspicious, you can copy the victim rows to spare rows. If you're careful, I think the overheads of this could be low. We actually proposed this in an ISCA 2019 paper called CROW, copy rows. And I like that idea, but its evaluation requires some more work going into the future.
Okay, thank you. The next question is from Kashif Nawaz. Is there a comparison between FDSOI and FinFET with respect to memory? Do you see any advantages of one over the other? Sorry.
Yeah, so that's a good question. Basically, I didn't want to go into the memory technology over here. Memory technology is really very, very different from logic technology. So what you mentioned over here does not apply as much. But if you go into the guts of the how DRAM is implemented, there are not many options that you have internally, and all of the major manufacturers have essentially converged into some technology internally so that they can manufacture the capacitor without a lot of leakage. So I think what you mentioned may be applicable to the access transistor, but there are bigger problems with the capacitor also in DRAM. Now, I'm not the right person to actually look into exactly device level solutions, but what I've read, what I've investigated points to the fact that whatever technology you implement internally is going to have difficulties with read disturb because you don't have enough isolation when you go into a density that's too large, basically. I hope that answers it. We can have more detailed discussion.
Okay, thank you. The next question is from Tony Pustinen. In 2020 and 2021, what can websites containing malicious JavaScript and WebGL cause a regular laptop or smartphone to do through Rowhammer? How browser vendors introduce any mitigation starting from year 2013?
Okay, that's a good question, but I don't think I know the answer. So essentially, I don't know is probably the right answer for both of the questions over here. As far as I know, I mean, I don't think browser vendors have introduced any solution specifically for Rowhammer, but I'm not sure if there are any attacks. And that's the difficulty of this. You don't know if you're being attacked, I believe, unless you're trying to figure out that you're being attacked.
Mm-hmm. Thank you. And from the same person, another question. On what levels can the para mitigation be implemented? Only BIOS?
So that's a good question. So basically, when we envisioned this, it was not BIOS. No, it was basically online in the memory controller. So you could actually do it completely transparently to the user, programmer, any kind of software in the memory controller. And that's, I believe, what was the best thing to do. Of course, Intel didn't do it because they wanted to give some option to the user I believe to give the confidence to the user that user decides what kind of vulnerability that they can tolerate. But yes, I believe it needs to be, the best solution is really, frankly, internally without exposing it to the user through the BIOS or some kind of programming framework.
Mm-hmm. Okay, thank you. The next question is from Moritz Josef from RWTH Aachen. What are the security considerations of 3D stacked memory in context of Rowhammer attacks? Intuitively, 3D stacked memory should be less secure than 2D RAM.
Yeah, so that's also a good question. I'm not sure why you think 3D stacked memory should be less secure than 2D DRAM, but basically the internal technology that's used to build 2D DRAM and 3D stacked DRAM is essentially the same. The DRAM chips are exactly the same internally, the layers, the interfaces are different. So in the end, the vulnerability should be, in my opinion, there, exactly the same, maybe worse depending on some conditions. I think one reason why it may be worse is there may be more noise and thermal issues in 3D stack. Maybe that's why you think that way. But I think more remains to be done to do the studies on 3D stack DRAM. But essentially, I would assume that it's going to be at least as bad as 2D DRAM.
Okay, thank you very much. And the last question so far from the audience is also from Thomas Hoberg. What about a per row transposition cipher of bits?
Okay, so I'm not sure if I understand this one very well. I think this is proposed as a potential solution, right?
Yes.
I don't know what the per row within the row, basically. I guess if I understand correctly, you're trying to transpose the bits within the row. I'm not sure if that's if you want to do that movement internally, I think it's not going to be easy within the row, because you need to basically read the row and write it back somehow by transposing. Now, with some support that we propose in DRAM chips to do better data reorganization movement, which are not part of the Rowhammer work, but which are independent, you could potentially make that. But you need to have changes to the DRAM chip to be able to do that.
Perfect. Thanks a lot. I think that's all questions from the audience. So if there are any questions from the panelists.
So I think I see something in the chat by Tony Pustinen. I don't think this was answered.
Okay.
So maybe I can unmute that.
Sure.
One person.
So is ECC RAM more or less vulnerable to Rowhammer than regular RAM memory? So that's a good question. So there are two types of ECC RAM. One is you have the same module, you add an ECC chip to it. In this case, there's no difference. Basically, your chips are vulnerable. Your ECC is also vulnerable to Rowhammer. ECC gets rid of some of the bit flips, but it can correct only 1-bit flip and detect 2-bit flips. But if you get 4-bit flips, like we have seen in Rowhammer studies, even as late as 2020, then you cannot basically fix it. So I wouldn't say it's more vulnerable. It's as vulnerable as the DRAM chip, but it's not able to. It's able to correct some of the bit flips, but it's not able to correct all of the bit flips. Now, some DRAM chips, like the LPDDR4 chips, incorporate in-chip on-die ECC today, and we have a lot of analyses of those on-die ECC chips. Again, on-die, these are single error correcting chips. They don't even detect the double errors. Again, because their technologies are scaled much lower to much lower technology nodes than earlier technologies, they're more vulnerable. But their correction capability doesn't benefit Rowhammer significantly because you can get more than 1-bit flip in a cache block. So hopefully that answers.
Yeah, I think that was the answer. Thanks a lot. So one more time, are there any questions from the panelists? You can also ask live if you like.
Okay, yeah, I have one question. So I think DDR5 RAMs are due this year. Any prediction on what kind of vulnerability you expect in DDR5?
That's a good question. I mean, clearly, we have not got our hands on DDR5 and we have not done the studies, but we are in touch with people who develop them and actually expect them. In my perspective, it's going to be more vulnerable because it's going to be a newer technology node. Fundamentally, the vulnerability will be higher. Now, DDR5 introduces, in my opinion, what is an unnecessarily complex and difficult to understand way of handling Rowhammer bit flips. They call it RFM, refresh management. You can think about this as the glorified TRR. I believe they're going to change this, I hope, at least. It's essentially another version of targeted row refresh that is a bit more sophisticated, but it doesn't tell you exactly how it works also in the DDR5 spec. So that's the solution that is being proposed, but I'm not sure if it's going to remain in the final standard going forward. My feeling is there needs to be some more research done so that we can have a much better solution. What I've seen in the DDR5 standard is not going to be that one, basically.
Okay, thank you. And maybe one more question. What do you think about ReRAMs or magnetic RAMs? Are they also going to have similar vulnerability, although they don't have capacitors, right?
So that's a great question also. So they don't have capacitor, absolutely. They have resistor, they're essentially resistive memories. But all of them are vulnerable to some sort of read disturb or write disturb phenomena also. I mean, I cannot go into the details and we have not done the studies, but there are some works that show that STT-MRAM has similar read disturb issues. I believe there was a work at ICCD a couple of years ago, for example, that talked about Rowhammer bit flips in STT-MRAM. I don't remember exactly how, if they tested real STT-MRAM chips, I doubt it. But I think at least from what we know, other memory technologies, as they scale to lower technology node sizes, they're going to have read disturbance and write disturbance effects. And if they're not somehow fixed, if they get exposed to the systems, then they're going to create similar vulnerabilities, in my opinion.
Okay, thank you. I think
we have one more question from the audience, from Thomas Hoberg again. The transposition wouldn't solve the flips, but the controllability.
Yeah, I think this is building on what we discussed earlier. If you do a transposition of the bits internally within a DRAM row by changing the DRAM architecture, yes, it won't solve the bit flips because, but basically, yes, it may make life difficult for an attacker, right? Basically, the attacker may not be able to figure out which bits they're going to flip, and they may not actually be able to mount the attack. So I agree with that. Although, I mean, in my opinion, I think it's better to solve the problem such that you get rid of the bit flips. Because, yes, you may play tricks such that attacker's life is harder, but again, the well-equipped attacker with the right motivation and with a strong motivation, can actually find out ways of overcoming not secure enough solutions. So I think it's better to, in the end, not expose these bit flips.
Thank you. And another question, is the memory on graphic cards, GDDR, vulnerable as well?
Yeah, so that's also a good question. So again, we did not do tests on GDDR, but as I mentioned earlier with 3D stacked memory, the underlying technology inside any of these under any of these interfaces is essentially the same. The DDR chips, the DRAM layers are essentially the same. And we are talking about a vulnerability at the DRAM layer, not at the interface. So I don't have any reason to believe that the GDDR is any less vulnerable. In fact, GDDR may be more vulnerable in the sense that the technology is vulnerable, maybe equally vulnerable. But with GDDR, you can, I believe GDDR reduces the latencies a little bit, row-to-row activate, back-to-back activate latencies a little bit. As a result, you can do more activates within a refresh interval.
Okay, perfect, thanks. And just a final comment from Thomas Hoberg from the previous question. He says every war is about economy,
yeah,
which I guess is true. I have maybe a final question if nothing comes in. So what are your thoughts looking a bit into the future in terms of in-memory computation and the role of Rowhammer?
Oh, okay, that's a great question. That's a completely other talk in memory computation,
yeah,
which I also give. But I mean, we're heavily working on in-memory computation as well. And clearly, as you get close to memory, your latencies get reduced. And in-memory computation may exacerbate some of these Rowhammer issues if you don't have a fix to the problem. So basically, I think what you're getting at is really, if you're close to memory, if you're doing a lot of row activates, you can perhaps do even more row activates within a refresh interval. And that is true, in my opinion, because I think in-memory computation could benefit from reducing the latencies of row activations as well. But I think I also see these as orthogonal issues to be solved. So regardless of whether or not you have in-memory computation, I believe you have to solve Rowhammer. You cannot really keep these bit flips getting out there and lingering. And I think the solutions to Rowhammer are going to be synergistic within memory computation, because if you can do computation in memory, you can also do intelligent solutions to fix the Rowhammer problem in memory in various ways.
Thank you very much. I agree definitely. Are there any questions left from the panelists or the audience? There's just another comment from Thomas Hoberg. He says, as you said initially, you have to model the physics to solve the problem.
Yeah, so I think that's one direction for solution. Certainly, if you can somehow model the physics very, very accurately, potentially you can come up with solutions. But I think that's a difficult issue to do for various reasons, because there's a lot of variation that you end up with in real manufactured circuitry. The models that you come up with in simulation usually are not as accurate as the real devices that come out after manufacturing, basically. That's why I think Rowhammer has not been an easy issue to discover previously. So I think the solutions, certainly modeling-based solutions can help. Physical modeling, I think, is very useful, but maybe a tough direction. But device-based modeling directions could be another direction, basically. You do these modeling based on the device characteristics after manufacturing without going into the physics level modeling. And you basically come up with models that can enable you to do better projection into the future in terms of exactly which parameters Rowhammer can be affected by. And then based on that, you can determine your vulnerability and come up with architectural solutions and design and testing solutions that can fix the problem based on those models.
Excellent. Thanks a lot. I think that's all from the questions in this case. And I think we are perfect in time, actually. So thanks a lot, Professor Mutlu, for the very interesting presentation. I think it's quite interesting to see that such an idea as Rowhammer, which at its core is actually quite simplistic, can have really tremendous security implications and, well, across all devices that we have nowadays. So thanks a lot once more for the presentation. And
thank you very much. I appreciate the invitation.